All right, Internet, welcome back. So this one was a doozy. I will be honest. This is definitely the hardest one I've come across. And it's not only a hard challenge, but the solution that I came across, the solutions that I've come across were actually hard to interpret and understand. So that took me a few days to wrap my head around each of the solutions that were provided and why they kind of manifested in the way that they did. Even with that being stated, there's still small bits of the solution that I'm not 100% sure why they exist, but they do. So that being stated, you and I will go on a journey together through this challenge. Now, this is called Gatekeeper, and this is Gatekeeper 1. So there's Gatekeeper 2, which we've obviously not done yet. And Gatekeeper 1 basically states that make it past the Gatekeeper and register as an entrant to pass the level. Remember what you've learned from telephone and token levels, and you can learn more about special functions such as gas left and Solidity's documentation. Those are our tips. This is our challenge. Now here is our code base, and I have it in VS Code as well. So I guess let's take a step back and really reflect on just how ridiculous this was. So when going through this, there's three different gates that we need to pass, which I kind of correlated to trolls. And we can see our trolls down here. It's a great photo I found on the Wikipedias that kind of explains the whole ethos of trolls and how trolls came to be and the origins of trolls. And apparently this image here is a reflection of some of the original, stories associated to trolls and this little fairy lady. Anywho, when looking for answers, I actually realized that what our faithful Web3 dev developer, YouTuber, actually didn't create a video for this. I'm not sure why, but this challenge was specifically skipped and he went straight to Gatekeeper 2 instead of 1. So this was not an option. We could not utilize that. So instead, I started searching for written solutions. And there was a series of written solutions, some of which were descriptive and useful, some of which were not. So this one here had the best description, which I'll walk you through in a second. But of all of these, I would say this one here had the best code that was actually useful for this version of Solidity that we're utilizing. And also this code was actually inspired by this code here. So you can kind of go back and forth between those two. Now, if I go into this resource here, I'm going to link all this below as per usual. This was, you can see, done back in 2018. This individual actually has walkthroughs for all the challenges, and most of them they're actually very thorough in the way that they're described, and they're actually really insightful. So I've actually read through some of these throughout the previous challenges, even though they're not necessarily completely applicable to the challenges we're doing in 2022 of April. Now in here, there's some explanations around what we're going to focus on and things like that. I'll bounce back and forth between this resource when going through the code and explaining it myself. With that being stated, we won't spend too much time on it now. Another resource that I came across was this, which is basically somebody having similar issues that we were having, walking through some of their kind of solutions in this stack form or this Open Zeppelin kind of discussion forum. This is the same concept, different person asking questions around the same solution. They came to an answer. But the way that they've come to answers in these solutions actually isn't the way that I've come to an answer, because the way that they've done it is trial and error through trying to find a certain part of the challenge. But what we're going to do is we're going to brute force it, which is going to take that piece out for us. This here, what is this? Okay, this is the code. This is the code that we're going to use that we've hijacked. And like I stated, they were inspired by this code here, but because you can see they basically put a thanks out to this person for pulling that code together. So if we go back here, we'll see that this code here is what this is linked out to. And they're basically going through something similar. And this bit here is the brute force piece that they basically used themselves in the other code that we're going to use. All right, so those are some of the resources. There's the beautiful trolls. And here's some explanations around what we're going to do here. So before I jump into the remaining portion of the notes, let's go back and actually look at the challenge. We'll keep that up for now. So here's our challenge code, and I have a bunch of stuff in VS Code, and I'll actually kind of give you a lay of the land here. I have tons and tons of notes throughout the code because I had to like reason my way through everything that was happening, both within the solution and the challenge to specifically understand how the solution interacted with the challenge. So that's what took me so long, is basically having to reason through every single piece of code to understand exactly what's happening. So I could then explain it to you, which is why I do these videos in the first place, so I could learn. Cool, so this is the challenge code and this is the target. So you can see there's a ridiculous number of notes in here that we'll review later, but below this I basically separated these out so we could just have the code and then we can have my notes above, because there's tons of notes and that get kind of convoluted and confusing. So this is our target and we'll walk through this quickly. So we have our version that's being compiled on. Remember, this is going to be 8.0, not 6, and this shouldn't be floating point, it should be static. We're going to import OpenZeppelin's safe math to do some different arithmetic down here. We have our contract, which is called Gatekeeper 1. Now in here we're going to set a few state variables. So we're going to have these state variables. So we're going to have our safe math imported, and it's going to be utilized on UINT 256. Then we're going to have an address called entrant. This piece I've included. I'll come back to this later, but this will be needed when you're doing this in 8.0 and above. So we'll skip that for now. Down here we have the modifier. So the modifier is, there have a few modifiers. So we have 1 modifier, 2 modifier, 3 modifiers. So these are our 3 trolls that we have to pass. Our first troll here in gate 1 is reminiscent of both, I think it's telephone and token. So we'll say tel and toke. So those are 2 challenges we've done historically. And really the solution here is something we've done historically. So this wasn't too bad, this first one. It's just ensuring that we're going to interact with this contract through another contract, so we're actually meeting the expectations here. Because what it's stating is it wants to ensure that the sender is not equal to the origin. So if we run that through our contract, so let me, I guess, draw it here. So there's a contract here, contract here. So when you send something here, this is the origin, and it comes back through here, and this is the sender. So if we ensure that the sender is not, so if the sender is not equal to the origin, continue. That's what the requirement here is for. So this is the sender, and this is the sender, and they're different, right? So this is sender 2, and this is sender 1. So if we have them, if we interact with them, they interact with us, then we're actually going to come in as the second sender instead of the first. So we're going to actually meet this requirement because we're going to use a similar solution to telephone. Simple copy and paste, basically. The next modifier. This one is the brute force function that we'll talk about later. But what we have to do is we have to ensure that the gas that's left is can be moduloed basically by this number to equal 0. And modulo means that you're going to basically take your number. There's a mathematical function called modulo, which is, I think it's a division or something like that, where you take a larger number and you incorporate the smaller number into it. And then if that equals 0, then you pass. So that's modulo that number. Google modulo if you don't understand it. It's a common thing in programming. You could also use a calculator to do it as well. But here, this method here, gas left, is something that they've incorporated documentation in the original challenge to kind of walk you through specifically what this means and how it's utilized. But basically, when you do a transaction and you're doing some sort of execution in a contract, there's usually some sort of gas left that's either sent back to you or then delegated elsewhere for additional execution. So whatever that gas is that's remaining, we need to ensure that it is that it fits this requirement here. So that is our second modifier. And then down here we have our third modifier. Now this one, I would say the modifier, this second troll here, I would say is slightly more difficult than this third troll. But for me, this third troll took a lot of effort to really reason through and understand specifically how we could pass all 3 of those requirements with the bytecode that we're going to use. So in this third troll or third modifier, we're going to input a key, and that key we're inputting has to pass all these requirements. So the first requirement for this key needs to say, okay, well, if this key is spliced down to UINT 16 and it's spliced down to UINT 32, so if we basically typecast this key, which actually one thing, sorry. So this says bytes 8 and this says UINT 64. Those are the same things. So bytes 8 is equal to 64 bits, right? So bits bi, bytes by. So those are the same. That was slightly confusing, but something I had to learn. Now, as we cast these in, we're going to cast this to UINT 16, which is 16 bits, and this is 32 bits. And then when you do that, you're going to cut basically your key in half and quarters and things like that. And when you do that, they need to equal here. I'll explain that further in my notes. This requirement here basically states that, okay, we're going to do the same thing. So we're going to cut it down to 32 here, and then we're going to then have the 64 variant of this. So we're not going to cut it down at all. And when we do that, we need to ensure that the 32 basically byte size is not equal to the 64 byte size. That's another consideration you have to take into when putting in this key or crafting this key to make sure it passes these requirements. And the last one is saying, okay, this key at size 32 should be equal to the origin uint, the uint 16 casting of the origin token that this was provided from. And that's going to be our token, or our key, I guess, or our account. So that's the third troll, the third modifier. And then all of this is then encapsulated into this enter function. So this enter function is what we're going to interact with. So we're going to enter our key here. When we enter our key here, it's going to basically say that you have to pass gate 1, gate 2, and gate 3 before we're going to return a Boolean that's true. So if you can pass all 3 gates with your gate key, then you're going to basically take your origin account and we're going to set it as the entrant, and then we're going to return true. And once you've done this, we're then going to pass, we'll pass the gate because we've gone through and we've shifted this from false to true, and it allows us in. So this bit here that I've included, the reason I've included this, and I don't know if I have this in my notes. Let me see if I have it in my notes. Okay, I do here. So this is everything you've seen below, just with a bunch of my notes incorporated. So this note here, you can see that I had to include the below addition. I spelled below wrong. Let's change that because, you know, grammar. Yeah, so in addition, blah, blah, blah. So the reason we're doing this is that point.a and above, you get an error. So if you try to do this without adding this line of code, earlier when you try to compile this target inside of Solidity, you'll get an error, and the error comes back and states that you're unable to actually cast an address to a uint. That's no longer allowed to do this, to cast address to uints. So to kind of get around this, I found this solution here, which I'll share with you. Let's say open. I'll share this kind of Stack Exchange resource, whatever, in the description. And you'll see basically they talk through how you need to utilize the casting of, is it this one? Yeah, it's this one. Yeah. You have to basically cast this prior to trying to cast it within the code. And we'll walk that through here. So we have our address. We're labeling it as an address. We're then going to cast that into uint 160. We're going to cast that into uint 256. And then we're going to place that into this variable. So once we've gone through all this, down here you'll see that I've not changed this in here, but in Remix I did. So let's go to Remix to make sure that's correct. So this is the target, same stuff, but in Remix, yeah, and you can see it here. So you can see that basically we've gone through all this trouble of doing the casting and setting it to this variable, and this variable is then placed right here. Instead of just putting the transaction origin there, we're going to put the I there, which has already been casted to a uint. So you can then cast that uint to a 16, and then everything works the way it should. So that's not really related to solving the challenge. I mean, it kind of is, but it's not directly related, and you have to do that to make sure you can actually just get it to function. So that is that piece. And I want to make sure I explain this in a way that's comprehensive. So we've set up our challenge. We can compile our target, which is great, and we've not talked about the attack code yet. We will talk about the attack code, I suppose, now. Let's get into it. And then there's some notes in here that I'll talk about specifically between the attack code and this. But I think explaining the attack code and then coming back to the explanations of why it works the way it works is going to be the most understandable way of explaining this. So we have our attack code here. So same per usual. We have our compiler. It's set to .8. We're going to import our target so we can utilize the enter function that we're going to call. And our contract's here. So our contract is are you the keymaster. So we're going to set a few state variables. So we're going to set useSafeMath because we're going to do some stuff down here, I think. This looks completely unnecessary, so I may delete that. But either way, we're importing SafeMath. In addition to that, we're going to set some other state variables. So this state variable here is going to be bytes 8, which is uint64. And it's a variable that's our account. So this is our account that's associated to the RankMe testnet. But you can see that it's not the entire length of the account. It's actually the second half of that number that we've cut off to fit into the uint16 requestment here. So we basically took our address. So say this is however long it is, and then we have our numbers here. Right? So say this is 64 bits, or 256 bits maybe, 64 bytes, something like that. Say it's a length of whatever. And what we're going to do is we're going to cut this in half, and we're going to keep the 0x. So the 0x stays, and then everything after the 0x up to the halfway point of whatever that number length is, and we can count it out here. So it's 2, 4, 6, 8, 10, 12, 14, 16. Okay, so 16, I think that's digits, which correlates to 64 bytes. Anyway, so we want to take 16 of the first half here, so the higher order bits. We want to take this and we want to cut it out. Once we've cut it out, we're going to have this smaller range here, which then fits into the 16 digits that are expected here. Hope that's understandable. And I'll explain to you exactly why we're doing that in a second. But just hold tight, that's kind of what we did there. Next is we're going to have another variable here called key, and that's going to be basically this variable and with this byte masking sequence, which the reason we're doing all of this stuff here is to pass gate 3. And that's basically passing all three of those requirements where we have to make sure that we're fitting into what's expected between the equals and the not equals, etc. And I'll explain this key in a second as well, but we're going to smash those together and put this into that key. Here we're going to initiate our contract, so we're going to have a variable that's public initiating off of the Gatekeeper 1, which is the contract sitting in our target. And then we're going to have our function here, which is passing, this is going to pass gate 1. So this is the telephone concept, where we're going to enter our target address. We're then going to incorporate that, and we're going to initiate the contract with that address and then put it into this variable. And that's going to allow us not to look as if we're the origin, but the sender instead. That's going to help us pass gate 1. And then the let me in function here, this is going to be related to gate 2. So this will be gate 2, which relates to the gas. Remember, we have to do the modulo piece for the gas to ensure that the gas left is moduloed by the number they provided. That's where this brute force comes into play. And this is different from some of the solutions that you'll see where some people just did a trial and error manually, and they checked on remix and kept on updating it until they found a number that fits the modulo of this number here. But instead of doing that, we're just going to brute force it, and it's going to be a lot faster and maybe more elegant, but I guess not. And inside of here, there's a few things happening, but I think the best way to explain this is via the notes that I have. But just know that this function here is doing a brute force to make sure that whatever gas that we have left over fits the modulo of what needs to be done here. So that, in a nutshell, is what's happening with the attack contract. But now I want to deep dive into different aspects of that so I can hopefully help you and kind of grok what I've grokked to understand specifically what's happening. So with Pat, we know this, so we can skip this piece. We don't need to talk about that. This piece here, we could talk about. So let's talk about the brute force, and then we'll talk about the. So we'll talk about gate 2, and then we'll talk about gate 3. Gate 2 is the gas. Gate 3 is the meeting the requirements for the byte stuff. So this one here, for the brute force. So let's walk through this one bit at a time. So the function is called let me in, and it's public. So there's a for loop at the top, and this for loop is basically saying I want to iterate all the way up to 120. And then I want to iterate one at a time. So we're going to say we're going to start with 0. And we're going to keep iterating over this. This is a common for loop syntax that you'll see in many languages. Now below this, we have a few different items happening here. So we're going to, okay, so this point here that I made is that we're going to use the low-level call method. Reason being is the reason we're using this low-level call method is it allows us to specify the amount of gas that we want to send or we want to iterate through. So the reason, so this is important to do so you can actually be specific with the gas you're providing. Next, some bits here. So in this for loop, it's basically stating that make sure that the result that's provided back So capture the result that's provided back. So that's going to be either true or false based off of the enter that we've called. And we know that because if we look at our attack contract here, we'll see that it's providing a true or false back, and that's what we're looking for to catch here. So when we're catching that, we're going to do that as well as we're going to take some data and put it into our memory so we can iterate through that loop if need be. We're going to have our address, which is what we established up here. That's going to be our target address initiated in the contract. And then we have our call method that I mentioned and the specific gas that we're going to iterate through. In this calculation here, so this is the part that I'm slightly confused on, I don't 100% understand, but I do understand, I think I understand, that this 3 here is associated to a push opcode, which is usually correlated to the add arithmetic identifier, I guess, basically, of saying I want to add these two things together, and that's how much gas that push opcode costs when running through Remix. This 819 is going to be correlated to the number they provided in the target contract, so that's nothing new, that's something they gave us. So we're going to times those together, then we're going to add 150 to that, and then we're going to add our iterator. So this here is going to start with 0, then it's going to be 1, then 2, and then 3, and then 4, and then 5, and 6, blah, blah, blah. We're going to keep iterating through that until we find something that, when all these combine together, is moduloed by this number down to 0. The thing I'm confused by is I'm not really sure what this 150 is and why it exists. I don't know what it's doing there. But it does have a purpose, I'm assuming. So one interesting bit about this this push code and this op code is I found a new feature that I've not used in Remix, which it's new to me, probably not to many other people though, is if you run things in the VM and we save this here. So if we run the attack and deploy it, under here, if we do let me in, and we debug that let me in, it shows you down here the specific opcodes that are being run as you iterate through that function. And you can see the different opcodes. Below that, you can see the associated fee for the gas of that opcode. So if I go down to push, depending on which push it is, you can see that it's set to 3 for that gas. It shows you the remaining gas too as you're iterating through this function. So other interesting bits here is it shows you some numbers associated to hex, and this is basically what's on the stack and what's in memory. One thing that I was doing earlier was hex to number, but I think it's hex to decimal. Yeah, here. So if you take the numbers here, so 0x88, I was just going back and forth and saying, okay, what does this mean and how much is this? So 136, and then I would basically bounce back and forth between the two to see what was the push opcode associated to this, and trying to grok in my head specifically what's happening here and basically what that means for each one of these steps. Yeah, so like here you have a bunch of, let's see, if I go through here and get to a push, so 096, and okay, so let's try this. So the reason I'm putting in 0x is, remember I said 0x never changes, so we're always going to keep this 0x here. But I'm going to add the last few digits here because everything else, all these zeros, is just padding. There's no really value there. And I think some of these actually start to make sense. So 0x96 is referring to the 150, so that we can grok that piece if that's how that matches up, and that's what's on the stack currently. 5FFD is 24573, and I think that is a big calculator. Let's do a small one. Is 8191 times 3. So 8191 times 3 is 24573, which correlates to this, which correlates to this 0x5 FFD thingy. And that's what this correlates here. So you can see on the stack, like, we're starting to grok what's there and why, not really why it's there, but what's there. So I thought that was interesting. I thought that was maybe insightful to share with you, that is a thing, and you can do that, and you can actually look at specifically what's on the stack and what push codes are being used and all that stuff. That was a bit of a diversion, but I hope that it was a useful diversion. So this is our gas. This is what we're iterating through. This is the formula that we're going to run through and try to get that modulo number out. Next, we're going to do an encoding of the ABI so we can actually interact with the enter contract. And with the enter, it specifically is called enter, and it has bytes 8 inside of it. So we're going to encode this via the ABI so we can actually interact with that bytecode. And then also we're gonna tack on our key, the key that it's seeking to be entered. So we're gonna enter our key into that encoded ABI. So we can actually interact with everything that we're interacting with through that loop as we iterate through it to make sure it's modulo correct. And then below that is basically saying that if the result that's provided back is true, meaning if we've actually succeeded in finding the right amount of gas that needs to be set, then I want you to break, and then you're finished. Like, you've completed the challenge, congratulations. If this comes back as false, then I want you to iterate back through the loop. And this will happen over and 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 over again until you find the right answer. And once it does, then it breaks out, and then it continues and says, congratulations, you're super duper awesome. So that's gate 2. We're brute forcing the gas. The next one is going to be the gate 3, I think. And that's when we're trying to basically figure out what specific hex string or masking that we need to then leverage. So if you go to this target section, I have a bunch of notes here that I think I've done a pretty good job at explaining how in the hell to pass gate 3. But before we jump into all that, we should take a step back and make sure that I've covered my notes that I wanted to cover. So in the detailed explanation that I've pointed out, not here, get out, this one here, they do a good job explaining to you specifically what opcodes, not what opcodes are, but how opcodes have associated gas with those opcodes. And you can see in the yellow paper here that was originally written for Ethereum, trust me, I can't read this, so I'm not a genius or anything. Genius, not a genius if you can read math, you just know how to read math. You can see that this symbol here is where gas is removed from the stack, and this symbol here is where gas is added to the stack. So this column here is add, this one subtract. And for an add function, you're subtracting 2 and adding 1. And that's going to be a total of 3, which is associated with the amount of gas one would have to spend. So that was interesting and helpful that I wanted to share. Now, masking. So this is around to gate 3. So gate 3 is all around the concept of byte masking, or masking generally. And to understand what masking is, I think this Wikipedia article does the best job that I could find that actually summarizes the concept of masking. And with masking, you're basically shifting bits back and forth, and you're converting the hexadecimal of two kind of strings. An example here, so we have 2 examples. The one that we actually care about and the one that we're going to use is going to be this one here that's masking bits by 0, and we're going to run an AND instead of an OR. But you can AND and OR 2, I don't know what to call it, I guess binary strings together to get out an alternative option or an alternative value. An example here is what they're doing is they're masking bits 2, 1 with an OR value. And the principle here you can see basically say is that when you combine whatever thing with 1, it equals 1, and if you combine anything with 0, it equals that thing. So that's kind of the OR structure here, and what that kind of comes out to. And you can see that manifested in this example here, where we have 1 and 1 equals 1, which correlates to what we said here. So anything plus 1 equals 1. Anything plus 0 equals that thing, which correlates here. So anything that comes here plus 0 equals that thing. That's here. So we can see 0 plus 1 equals 1. 0 plus 1 equals 1, 1 plus 1 equals 1, so that all matches. Same thing here, 1 and 1, 1, 0, 1 equals that thing, 1 and 1 is 1, 0 and that thing equals that thing. And then you basically have an output value here, because we didn't, 0 and 0 equals the thing, 1 and 1 equals 1, 0, 0, 0, okay, it's all the same, that's good. So when you OR these binaries together, you get out a new value, which is a new masked value. This is masked. Same thing applies for the zeros, but this is the one that we care about, because what we're going to do is we're going to do this to ours. And this is basically stating as masked off, 0 masked. So they call this as masked off, and then masked on with a 1. So masked off is 0, masked on is 1. And the way that this manifests, and the principle kind of works, is you have that anything and 0 equals 0. And here with the 1 is anything and 1 equals that thing. So this is basically the opposite of what we've done historically with the bits of 1 and the OR. This is the opposite with the AND method. So we're going to basically do the same thing here. So we're going to say 1 and 0 equals 0, because remember anything and 0 equals 0. So this is another 0, this is 0, this is 0. So everything is zeroed out here. This is going to be 0, 1, and any one thing is 1. So that's going to be that here. And actually, let me take a step back. So this is going to be, for both of these, the first thing is going to be the thing that we're going to mask. The second thing is going to be the mask itself. And the third thing is going to be the kind of the output of whatever those two things are combined. So that's a good thing to point out and understand. And I'll talk about that in the answer as well. So we have that set up. So we've kind of understood that here. The same process applies here to what we've just discussed. And then we have that output value here. So with masking, that's kind of like the down details of what's happening and a more intuitive understanding of what's happening and looking at specifically how this manifests in images, because this is utilized in images and different types of like editing software for images and videos. As you can see, this is one option and this is the second option. So this first option is doing an and as it goes through this, it takes the original value. So this is like the original value. This is the mask we're going to apply to it. And this here is going to be the output. And the same thing applies to this over here for all of these. We can see when we put the original image in, we're doing an and here. So this is an and this is going to be an or. So we do an and, we combine these two, and then we get out this output, and we do the same process here. We add this original value, which is originated from here. We add this, and then we get back our original, actually not original, but something new. So we OR these together, and we get this. And that's kind of an intuitive understanding of how, even with images, you can adjust all the bits in a way that manifests into an interesting image that can be used elsewhere. And that's a practical use for this. Cool. That was a lot of talking for just explaining kind of the basics of what's going on, but it took forever to understand what was going on, so I thought it would be useful to kind of give you the down low so you didn't have to struggle as much as I did. Okie dokie. So with that being stated, let's walk through this. Let's walk through this together, one at a time. So the first requirement here is we need to get a key first, right? So that's the first step that I kind of like skipped over and confused myself with, is we need to get a key. And to get our key, if we look at our attack here, our key is going to be a few things. It's going to be our origin, a 16-digit variant of that. So we've already talked through what this is. So it's your account sliced in half to 16 digits. So that's what that is. So we understand that. The next part is taking this thing that we're going to get to and understand, and we're going to combine that with that, which is going to make our key. So that's what the key is here. So let's figure out how we got to that hex number. How did we get to this here? Well, let's look through this. So to pass these requirements, whatever key that we have, whatever that is, we need to ensure that the 32-bit version of that and the 16-bit version of that match. So to look at what that would look like, I have some notes here. So we have some values, right? So we have, this is the 32-bit variant of something, and this is the 16-bit variant of something. And if we compare these together, this 0000FFFF would match with this if they combined. Reason being is when you combined a 32-bit, so this is a larger number, so if you combine a larger thing with a smaller thing, what's going to happen is you're going to basically it was discard the higher bits, and the higher order bits within a hexadecimal array thing like this is going to be the bits on the left hand side, so closer to the X. So this section here, these are the higher order bits, and we're going to knock these out. And when we knock these out, then you can see that when we compare these are identical. So we have 4Fs and 0X, and that passes the first requirement. So we can see the 32-bit length and the 16-bit length do match when compared this way. And that's how that rolls. And the reason I knew that it discarded the left-hand bits is because I did a bunch of research and I got super confused, and I found a few resources that I'll share with you. So this Stack Exchange talks through specifically typecasting, and then down here there is a mention that you can see that when assigning 32 to 16 simply discards the higher order bits. And then I did a bit more research and found this Stack Exchange that talks through lower and higher order bits, specifically what they mean and how they exist and all that good jazz. So that was useful, and that's why I knew what that meant, how to explain it. Cool. So we have that understanding. Groovy. So with that being said, we know that if we compare this with this, and so this is actually going to be part of our key. So this is the last 4 digits of our account. So we're going to have, 4 zeros, last 4 digits of our account compared against the last 4 digits of our account, and we know that this is discarded, so those match. So that's a good check. We've gotten past the first sub-troll of the third troll. The second one here is basically stating that the 32-bit size of our hex cannot be this, when compared, cannot equal the 64-bit size of our hex. So with this, we're actually not going to AND this stuff together. Instead, we're going to have the ones attached to it. So that's I think that's the mask on approach, or the mask, or I don't know. I think it's a mask on approach. And you can see instead of filling it with zeros, we're going to fill it with Fs. So when you do that, we know that these will not match. Because if you look at the example here, the 64-bit solution and the 32-bit solution, when compared, they cannot match. Reason being is that this has a bunch of different values that are not basically padded like this. So when you do expand this out, they're unable to match, and they wouldn't equal the same thing. So I hope that makes sense. But if not, you should definitely try to grok this yourself, because it is insightful to understand kind of how masking works within this hex section here. So that's the second one we passed. Like, congratulations, you got the sub troll 2, and then sub troll 3 is saying that the 32-bit size of our key has to equal the origin value of a uint16 variant of that. So we have, going back to the stuff that we discussed in our attack contract, this is me copying and pasting that here, and we can see that we have the 16 digits of our account, which is in this variable, and then we're going to AND it with that. So I have it written out here to help you understand specifically what the AND looks like here. So remember how we talked through the image, right? So we have our original value, we have our mask, and then we have our output. And our output is going to be our key. So original value is going to be the last 16 digits of our account. The mask is going to be that hexadecimal value that we've derived from the two stages up here. So after going through this stage and this stage, we know that this hex is going to pass both of these stages based off of the comparisons that we have to pass for the requirements. So we have that here for a mask, and then we're going to AND these together. So when we do this, remember, 1 and anything is going to equal that thing when you do the AND, and this goes back to the Wikipedia article that we just walked through. So we're going to go through this, and we're going to basically get all the values associated to that above. We're going to then do 0 against all these things, and that's going to zero that out with the AND. And then we're going to do 1 for all these things, and we're going to get those last 4 digits. So this here is our key, and this is what we're going to pass into our eventual attack here to go through the stages. And like we said, so the last stage here for the third requirement is saying the 32-bit size and the uint16 size of this have to equal each other. Well, we can see here that the 32-bit size of our mask, which is going to be the last bits here, so it's going to be this section starting here to here, which is what you're seeing there. So we have this equals this, and the reason that if we can compare these, remember, when we compare a higher to a lower, these are discarded, right? And that means when you compare these two, they're going to be identical, similar to the pass that we passed here. So with all that said, and all that hard work of grokking, we will actually pass the requirements for gate 3 to get all the way through. And with that being stated, that was a ridiculous amount of talking, and I want to make sure that I didn't miss anything. I didn't. Okay. Well, internet, I hope you're still with me, because that was painful for me just to explain, and I hope that it was hopefully somewhat insightful for you. All right, so what I'm going to do is we're going to run this, and we're going to get our answer, and we're going to end this challenge, hopefully. So I want to make sure that I'm in the right setup, and I'm doing the right thing here. So contract ABI. So if we look at our ABI here, we can see that in here we have an enter and entrant. Our entrant is public, an address that we cannot publicly see, and our enter is the function that we're going to call down here. So if we look at the entrant contract, we can see that this is set up to all zeros, so that is going to be a false. So currently this is set to false, and we're unable to actually go through. We have to change that to true, which is going to be this value change here. All right, with that being stated, we need the address. That's our target. So we'll go to Remix, and we have our attack contract open, so we'll deploy this. Took a little longer than I thought it would. I got a little nervous there, Internet. Alright, so it's deployed, and now we're going to take the target address, we're going to put it into the set gatekeeper, which is going to be this function here. So we're going to put our address in here, it's going to then initiate the contract and tack it onto here so we can pass the initial gate 1. So we're not being, the sender is not equal to the origin, so we're going to pass that piece there. That's done. So if we do get GP, whatever that, Gatekeeper, Gatekeeper 1. Alright. So we can see this is the address. And that's the address that we input here. So that's set up correctly, and we can see that this variable is set correctly. Now, the final stage is going to be saying, let me in. And when we call let me in, it will then iterate through this entire process. It will call enter, it will input our key, which we've derived up here, that went through our process of understanding how the key works and how the hexadecimal match works and all that stuff. We're going to input the key, we're going to hopefully set the right gas through our brute force, and once we've done all that, we should, in theory, have completed the challenge. So if we go to entrant, we can see the entrant is currently set to our password, so that means that we've passed it. So if we submit instance, we should have beat it. Boom, we did it. Congratulations, Gatekeeper 1, level completed. This was not an easy level, a lot of stuff to understand in Grok, but I hopefully have provided some intuitive understanding for those out there that were just as lost as me. That being stated, I will see you on Gatekeeper 2.